Welcome to The Explainer. Today, we're exploring a seriously mind-bending concept that sits right at the intersection of neuroscience and silicon. We're talking about neuromorphic computing. To set the stage here, I want you to picture a massive humming power plant, just churning out megawatts of electricity. Got it? Okay, now picture a single, dim, 20-watt light bulb. Well, what if I told you that the light bulb is currently vastly outperforming the power plant at the absolute most complex processing tasks in the known universe? It's true. Your brain, yes, even on a groggy Monday morning, is doing vastly more complex processing than our most advanced supercomputers, and that is exactly the incredible reality we're unpacking today. Okay, let's dive into this. Here is our roadmap for The Explainer. Number 1, we'll look at the AI energy crisis. Number 2, biology as a blueprint. Number 3, building brains in silicon. Number 4, real-world applications. And finally, number 5, challenges and the future. So starting off with Section 1, the AI energy crisis, unsustainable power. Right now, we are facing a massive, fundamental paradox in modern technology. Our progress in AI is just staggering, but we are hitting a really hard wall when it comes to energy. It's totally unsustainable. I mean, training a single large language model consumes hundreds of megawatt hours. To put that in perspective, that is roughly the yearly electricity usage of multiple households, just for one training run. Meanwhile, your brain performs infinitely more complex sensory fusion, pattern recognition, and real-time reasoning, all while running on roughly 20 watts, literally the power of a dim light bulb. So to solve this monumental energy crisis, we basically have to rethink the entire foundation of computing. Moving to Section 2, biology as a blueprint, nature's efficiency. To understand how the brain acts as this ultimate blueprint, we really need to zoom in on its fundamental binary unit, the action potential. So conventional computers are always processing continuous streams of data, right? But a biological neuron doesn't work like that. It actually maintains a resting state of about -70 millivolts. It's mostly just sitting there, quiet. It doesn't fire constantly. But when incoming signals push it past a certain threshold, boom, it generates this rapid, stereotypical voltage spike up to +40 millivolts. This right here is the biological bit. The absolute secret to the brain's extreme efficiency is that neurons use sparse, asynchronous, event-driven spikes. Most of your brain is actually quiet most of the time. It only spends energy when there's a specific event worth communicating. Let's move to and see how this builds. Because when a neuron fires that rapid spike, something pretty magical happens at the connection points, which are called synapses. This process is called spike timing dependent plasticity, or STDP for short. Essentially, synapses adapt locally, based entirely on the precise timing of these spikes. So if a presynaptic neuron consistently fires right before a postsynaptic neuron, that connection gets stronger. If it fires after, it weakens. And this is the biological basis of learning. The best part? It requires absolutely zero energy-hungry global error signals, which, is exactly how traditional AI has to learn. Which brings us to Section 3, building brains in silicon. Neuromorphic hardware. So, how do we actually translate these biological miracles into physical hardware? Well, first we have to step completely away from the von Neumann architecture. That's the design behind nearly every single computer you own, and it has a fatal flaw. The CPU and the memory are totally separate. Every time you want to compute something, you have to fetch data back and forth across a bus. It wastes immense amounts of energy. We call this the von Neumann bottleneck. Now, contrast that with neuromorphic in-memory computing. In your brain, the synapse is simultaneously the memory storage and the computational processor. They are the exact same thing. By co-locating memory and computation like this, neuromorphic chips completely eliminate that memory processor divide, saving just a staggering amount of power. And this introduces us to spiking neural networks, or SNNs. You can think of SNNs as the third generation of artificial intelligence. Unlike traditional deep learning networks, which use continuous numbers and literally run constantly, SNNs communicate through discrete binary spikes that unfold dynamically over real time. Just like your brain, an SNN stays completely silent until an input arrives. That's where the massive power savings come from. But to function optimally and actually deliver those savings, SNNs require specialized, biologically inspired hardware to run on. Enter the memristor. This is absolutely one of the most exciting components of neuromorphic hardware today. A memristor, or memory resistor, actually retains its resistance state even when the power is turned off. They can be built from phase change materials or even these ultra-thin 2D heterostructures. and they act perfectly as artificial synapses, enabling that in-memory computation at incredible speeds. Literally, just by applying a voltage, the physical resistance of the memristor dynamically changes. It mimics exactly how biological synapses strengthen or weaken during learning. It's a real game changer. Now, this field didn't just appear overnight. Back in the 1980s, Caltech's Carver Mead actually coined the term neuromorphic when he noticed that transistors operating below their normal switching voltage behaved exactly like biological ion channels. Fast forward to 2014, and IBM fabricated the True North chip. They managed to pack 1 million neurons into just 65 milliwatts of power, and the progress is accelerating incredibly fast. By 2024, Intel announced HelloPoint, which is a staggering system housing 1.15 billion artificial neurons. The scale up here is just phenomenal.
All right, Section 4, Real-World Applications, Beyond the Lab.
So all the silicon theory is fascinating, but what is it actually doing in the real world? Let's bring this home. Imagine an Internet of Things device in your smart home that can run keyword detection for weeks on a tiny little coin cell battery. Or consider autonomous vehicles. They are using dynamic vision sensors that act like artificial retinas, processing visual changes in microseconds with near zero power. In healthcare, researchers at ETH Zurich have already developed a real-time epilepsy monitor using neuromorphic hardware. It's even leaving the planet, literally. BrainChip's Akita 2.0 architecture was licensed by NASA for space-grade AI platforms where power is, as you can imagine, extremely limited. So the crucial point is, it all comes down to power. Take a look at this. When you are training massive language models, conventional GPUs taking 300 to 700 watts absolutely dominate the landscape. They win. But when you move to the edge, to sensory processing, real-time adaptation, and autonomous systems, neuromorphic architectures just crush them. We're talking about operating on just 0.1 to 5 watts. And they achieve this by using that completely different event-driven architecture and co-located memory we talked about earlier. Let me just punch in this incredible statistic to really put this into perspective. 42,460, that is the number of frames per joule achieved by IBM's North Pole inference architecture. By eliminating that off-chip memory access, it is 25 times more efficient than a traditional high-end GPU. And the real kicker? It operates so efficiently that it doesn't even need liquid cooling. Think about that. Finally, Section 5, Challenges and the Future, What Lies Ahead. As exciting as all of this is, we definitely need to pivot to the horizon because there are some enormous hurdles here. Scalability is a massive challenge. Intel's HelloPoint hit 1.5 billion neurons, right? But the human brain has 86 billion. Bridging that gap means we have to conquer totally new materials and 3D stacking. Plus, there's a complete lack of standardization in the industry right now. There's no universal x86 equivalent for spiking neural networks yet. Every chip essentially has its own software. On top of that, training non-differentiable spiking neural networks is highly complex. And those amazing new analog materials like memristors often introduce cycle-to-cycle noise that engineers are quite literally still trying to tame. We also have to objectively consider the stakes derived from this extreme efficiency. Ultra-low power, always-on sensors could easily enable pervasive, continuous surveillance without anyone ever needing to change a battery. In the defense sector, autonomous systems might start making decisions at microsecond timescales, which raises huge questions about accountability and human oversight. Additionally, as these chips interface directly with biological neural tissue, like in neuroprosthetics, the capacity for brain-machine communication brings up a whole new set of complex questions regarding cognitive influence that are going to require very careful, measured thought from all of us. Which leaves us with this final, profound question to ponder. Will the ultimate future of artificial intelligence look exactly like us? The human brain still remains the most efficient, adaptive computing system known to science. As we push the absolute physical limits of traditional silicon, it seems increasingly likely that true, highly efficient artificial intelligence will inevitably require a biological blueprint. I really hope this explainer sparked your curiosity about this incredible convergence of neuroscience and computing. Thanks for joining me, keep learning, and I'll see you next time.